Are we live? Okay, looks like we're live. All right. Hello to everybody that's here, and hello to everybody that's watching in the future. Thank you for joining. We'll jump right into it. I wrote down the goals for today's stream here. So as I mentioned in the title, as well as wherever I posted about it, the goal for today's stream was supposed to be optimization. And so we're going to focus on what we were dealing with yesterday. Well, let's actually write that down. The training was effectively happening at about 600 iterations per second. Right. So we're working through the environment at 600 frames per second. And that's not necessarily very fast. Let me log into weights and biases, and we'll go over what that translates to in terms of time. Okay, I need to turn dark reader off here. So I believe this was my last run. Let me ensure that. Right, so this was a run that I started during the stream, and then it kind of kept going over time, and I stopped it after about 1.4 million steps. Now, there's like a sweet spot, some balance between epsilon and the actual model where we achieve a pretty good reward. All of this is way above what the environment considers as like a solution level, right? So this just works. Solution is supposed to be at a score of 200. So we're beating that very, very easily. But if we look at the time, this 1 million steps took about 35 minutes. Now, I would like to set this environment up. I'd like to see it, hit that maximum score of the environment of 500. So even though the win condition is described at 200, I want to push it up to 500 and sort of squeeze as much performance out of it as possible. And so there's a few different ways to do that. One of the things that that is a bottleneck right now is the fact that we are training on CPU. Right, so that's the first task, is to change that. I have a CUDA enabled GPU. I have a 1070 Ti, so I'm going to put the training as well as the forward inference on the GPU. So that's step number one. Step two, we had some conversation yesterday too, and it might come up today, but we talked about the replay buffer, which is right over here. And the replay buffer, we first implemented it as a list, right? So anytime there was an insertion, there's still commented code from there. We were simply just keeping the last, buffer size elements. And that was fine, but it was slow. It was slow in insertion. It wasn't slow in sampling. Sampling from a fixed length list is pretty fast. But insertion in this case was order n, and that's terrible. So we switched the implementation to a DQ, which is a doubly linked list. And the nice thing about DQ is now that insertion, which is the more common operation, is now order 1. However, sampling, which isn't as common as insertion but it still happens, is order n. And that also slows us down. So the second bullet here is to make the replay buffer faster. And the way that I'm going to try to do that is by keeping a fixed length buffer. And then, excuse me one moment. So by keeping a fixed length buffer and sort of having the insertion happen on the buffer on a rolling basis, right? And then it'll just always be the same length array. Insertion will be order 1, and then sampling will also remain efficient. It wouldn't be order n. So that's the second task. With these two done, the hope is that the 600 iterations per second would be pushed up to a much higher number, hopefully something like 2,000-3,000 iterations per second or higher. So with that, the training time should be brought down a lot, and we can do some hyperparameter tuning, which is gonna mostly be about changing the epsilon decay rate and maybe the learning rate, and just try to push this cartpole environment to the maximum score. And then there's a stretch goal. I'm probably not going to get to it tonight, but I'll try sometime in the future. But right now we're only running one environment. It's sort of in a serial mode on a single thread. So a stretch goal would be to change this to multiple environments. And Ray is a library that makes Python multiprocessing a lot more straightforward. So let's get going. Okay, so Pytorch is different from libraries like TensorFlow and Keras in how it handles GPU. In TensorFlow, you have a package called, a normal package called TensorFlow, and that runs on CPU, and then another package called TensorFlow-GPU, which will run your code on CUDA. It'll try to run it by default, but you can turn that off with environment variable and stuff like that. Pytorch doesn't do that. There's one package. However, whenever you want to put something on GPU, you essentially have to tell both the network and the data that it needs to go to a different device, right? So let me open this documentation here. So right here, when we define a tensor, normally if you define a tensor, it'll go by default on CPU. But during the definition, we can tell it that it needs to reside on a particular device. In this case, that device can be a normal CUDA device, or if you have multiple GPUs, that it can be GPU 1, GPU 2, etc. And then a tensor that already resides on the CPU, we can put on the GPU by calling this .CUDA function on it. This is what we're going to end up using for the most part, because we have a storage and an in-memory store, and we want that in-memory store to stay in CPU land. Similarly, I don't know if there's an example here for the network. Here we go. So when we have a network defined in Pytorch, we also need to specifically put that network on a separate device. So the device here can actually just be a string. So we can just make that an argument for the main function. And let's by default put that to CUDA now. Okay. Right, so now when we create the model, we can say, hey, this model should now go on to device. Now, one of the things that'll happen here, if I just make this change and don't change anything else, if I run my file, it's going to crash, right? And actually, hang on, let me make sure this is running in test mode. I also want to make sure this is running in train mode. So we can turn weights and biases off right now so that it doesn't get in the way. Okay, so, whoa. Where'd that trace back go? There we go. All right, so expected object of device type CUDA, but got device type CPU for something. In this case, this is like a matrix addition. So this is probably happening in a forward pass somewhere. So this happens now because we put the network, where did it go? Here we go. So we made the network object, we put it on the device. And then, oh, and the target network also needs to go to the device. And then we have the replay buffer. We sort of go through, play the first few, 5,000 or whatever steps. Oh, actually, even here. So right here is where our troubles start. So when we call the model to get our action, this torch.tensor immediately puts last observation onto the CPU. So we want to set device equals to device. So now that won't fail. And then environment stepping doesn't matter. This is all fine. So all of this will remain fine all the way until we get to the train step, right? And now in the train step, we need to add, it's probably good to add another argument here that tells us what device to use. And now, as we make our tensors, we can put them on the device. So it's a small change, and initially it seems kind of annoying, but I've grown to like it because it gives me a lot more flexibility about where I put the data and where the network runs, which ends up being actually very useful later on. Okay, so we run the target network. Everything is on the right device now. This is already on the right device. With the actions, when we do one hot, now this one hot should go to the GPU, and then the loss calculation, all of these various pieces are already on the GPU, so we don't need to do anything more. This is fine. I think the one place where we might run into some trouble, let's find out, is, let's say loss equals train step. Oh no, this is, yeah, I think I might need to, and I'm just going to preemptively do it. I might need to call CPU on this because this loss value is not a float or a scalar. It's actually a torch tensor, and so before I was calling detach an item on it so that it can be rid of any gradient information, and then you just get the one item that's contained in this tensor. Calling CPU on it will also ensure that that we take it off of any other device. If it's already on the CPU, this call is not going to do anything. So there's no harm in doing it this way. Okay, this should now make it so that our training runs on the GPU. One of the things that I like to do is run this command, watch-n0.25, and pass it NVIDIA-SMI. So this is, of course, currently we're focusing on CUDA, so it's only going to work on an NVIDIA GPU. NVIDIA SMI just gives you an overall sort of what's going on your GPU. So how much of the memory is taken right now, what is the utilization? And the utilization actually right now is really high. I just realized that because the encoding on my screen capture software is happening from the GPU. So this might actually become a problem. We'll find out. But right now there's no Python operations running, so we can go ahead and now run agent. Nope. There was an error. So let's go ahead and kill this guy for now and just make sure that all of our bugs are done. Action equals device equals device. CPU was passed device type CUDA. Oh, I think this should also be done as a 2. All right, let's try again. Okay, great. So already there's a difference. We started off with 600 iterations per second, and by simply putting the forward pass on the GPU, forward and backwards pass on the GPU, we are now at about 1,000 iterations per second. So yay, first speed up. I'm not. This is dry run mode, so it's not actually putting it on weights and biases. So let's see. Now, one of the things that is true here that we currently can't really do anything about, that's what the stretch goal is about, is that doing this, doing the forward pass where, you know, neural networks, especially on GPU, they work better if you're doing a forward pass in a batch. In reinforcement learning, when you only have one environment that you're dealing with, it's not quite doable. You can't quite do the forward pass in a batch because you're just running one environment. So the batch size is always going to be one because the action you have to sample every single time, or however many time as required by epsilon. And so we can't do much speed up for this. Right? One of the things that we could do is we could change how often we train, right? So right now we're going through 100 steps of the environment before we train once. We could potentially change this so that we go through 500 steps of the environment and train on a larger batch, for example, right? So let's do a couple of things. So we're gonna change the size of memory. So memory size, let's set that to 500,000, so 500,000. And then minimum size before starting, we can up this as well to 20,000. And then the sample size, let's up this to something like 7,500, so much bigger. This will make the backwards pass a little bit, not necessarily faster, just more efficient because we're using a bigger sample. And then we can make it so that the target model update happens because this sample size is much bigger. I think it's okay to be a little bit more aggressive with this. We'll find out. So this is going to be like after 100. So that's like 7,500. Oh, no, it's so yeah, it's 100, and then that's going to change based on the environment steps. So we can say go through 1,000 steps in the environment before you actually do training, and then do training on a larger batch. This might make things a little bit faster. In this case, it's going to also make it so that the target model update only happens after 100,000 steps. I think that's fine. Well, I guess we'll find out. So when db on, and let's run this. And I'm going to open that NVIDIA SMI thing again because it's useful to look at the memory consumption. I don't have I have a commodity GPU. It doesn't have a lot of memory. It has 8 gigabytes of RAM, which is nice. Oh, and look at that. So by doing this, by changing the semantics of how we're using our hardware, we're now at about 3,000 iterations per second. And it dips below a little bit. The dips are probably happening because of the training, right? So every time you actually call a train step. But yeah, so this is now running significantly faster. Now, if that, we still have to see what that translates into in terms of how fast the model converges. So that there's two things to consider, right? How many steps of the environment do you have to go through versus how much real time passes before you start getting good results. So let's look at the dashboard real quick before we move forward. And I'm going to go ahead and get rid of all the runs except for the last one that we started off with at the beginning of the stream. If it would just visualize. Did I keep the wrong one? Apparently it has no data. So never mind. Let's just get rid of this one too. Okay, so we can leave this running in the background and see if it if it's going to be giving any reasonable results. And we can move on to the second optimization, which might not end up being that big of an optimization this time around. And that's because now that we're waiting, let's see, we're waiting 1,000 steps now before we sample. So the actual time that's taken during the sampling might not be enough for us to worry. But let's try to figure that out anyway. So now one of the really nice things about passing this as a parameter is that I can potentially run another instance and not run it on the GPU, or I can run it on the GPU. Either way would be fine. So I can leave this training, and then in cases where this was like really resource consuming, like if it was taking over the entire GPU, in this case it's not, I would still be able to run another instance to do some testing. Oh, interesting. So this has to be sampling, right? So we started off with about 3,000 iterations per second, and it's gone down to an average of what it appears to be about 2,000 iterations per second. So this, I'm like reasonably sure that this is happening because of the sampling. So I'm not even going to run a test. Let's just go and try to, so this got done. Let's go and try to make the replay buffer faster. So the idea behind making the replay buffer faster is to not use a DQ. Instead, we will allocate an array filled with nuns initially. And then we will also keep an index. The point now is that every time we insert a new element into the buffer, we, instead of doing an append, the index is the sort of the current location. So we can say self.buffer at self.idx equals, oh no, it shouldn't just be self.idx. So yeah, it's going to be self.idx modded with self.buffer size. And you'll see in a second why. So this gives us essentially a rolling index to the buffer. So once the IDX becomes equal to buffer size, we spill over the buffer and we go back to the beginning. Right. So we do this, and then we set that element equals to whatever that was passed. Okay. So now we no longer ever have to worry about pushing items off of the buffer, because they're always like, we're just going to reuse areas in the buffer. So the insertion is straightforward. The sampling becomes a little bit more complex, but not too complex. Basically, there's two modes or two phases in sampling. So one of the phases is when the index is less than buffer size. So if self.idx is less than self.buffer size, this is important because in this initial phase, right? So the memory size that we're setting is like 500,000. So in this initial phase, until we reach 500,000, we can't sample from the entire array. We can't sample from the entire array because we've allocated an array of nuns, so we can only sample up to self.idx, right? So in doing so, hello in chat. Hi, Live Village. So this assert also needs to change, because we're no longer just dealing with self.buffer. So essentially, we need to assert that the number of samples that you're asking needs to be less than or equal to the current index minus 1, I think. Or I think it's just less than in this case. So that needs to be less than the index the, let's see, the minimum of the index and self.buffer size. Now what this will do is, because index is just always gonna keep increasing, we will, up until it hits the buffer size, we'll go ahead and check against just the index, and then as soon as it hits the buffer size, then we'll always be checking against the buffer size. Okay. So now there's two phases in the sampling. So if the index is less than buffer size, then we need to sample from the first bit, like the first, essentially a subarray. So it's going to be the array up to self.index. Right. Oh, and when we insert, we also need to increment index. Okay. And then if that if is going to be false, then we sample from the entire array. So we have taken an implementation that was done with a doubly linked list, and we have replaced it with a fixed size array. Insertion is now order 1 because we simply assign an element, and sample is now order num samples, as opposed to being order m or n. So let's look at our CUDA-based training and see if it's improving. It is not. But it's going fast. Yeah, so we were able to hit 1 million steps in less than 10 minutes, like 8 minutes. So yeah, it's definitely fast, but in sort of trying to achieve that speed, we also have lost. And that's probably happening because we're not training as often. So let's go back to the hyperparameters. Gonna kill this. With the replay buffer, we should get some benefits here as well. So bigger sample size is probably fine. This probably should not matter. But the environment steps before train, setting that to 1,000 may have been too insane. So we can cut that back down to 100 because we know 100 worked, right? Or at least was working last time. So with that, we can go ahead and run it again. Oh, something's wrong with the replay buffer. Dim sample is less than min self IDX. So instead of throwing an assertion, let's actually put a debugger in there. So if num samples is greater than import IPDB, IPDB.set trace. Okay, let's run this again. Do some debugging. Okay, so let's see. How many samples did we ask for? This should be 7,500, so that is correct. What is self.idx? Self.idx is 101. So we're not letting the replay buffer fill up. Did something go wrong? Let's see. RB equals replay buffer, while true. Oh. Okay. Yeah, I know what's going on. This is based on length of the replay buffer. This is a problem. So essentially last time when we put all of this together, we were going by the length of the buffer object under replay buffer right here. And now that's because that's always going to be fixed. It will always be greater than min or b size. So it starts trying to train. We can fix this. Let's see. We can't look at, we can look at IDX. Yeah. So instead of looking at the length of the buffer, we can now just look at index. Right. That should do it. Hi, Grav Vals, and hi, Brian. Thank you for joining the stream. All right, let's see if this is going to work now. Oh, wow, it is super slow. It's slower than it was before. What's going on? Oh, of course it's slower than it was before. I created an unfair situation. We left the batch size the same at 7,500, and then, but we're training after 100 environment steps. So this might have potentially better training dynamics, but that's not good. We still wanted to run through new environment samples fast because the epsilon value, this epsilon value, we do want it to decay to a very small number by the time we get really close to the end of the training, because that will help the system sort of excite all the various possibilities better. So this is going to probably slow us down again, but let's change the sample size. We can change it back to, we can change it to 750 for now and see what that does. Okay, so that seems reasonably fast. It's about 6 times faster than we were doing before. By before I mean last night. And the performance of this, I think, should not degrade that much over time, because the replay buffer is a little bit smarter. So hopefully it won't degrade. We'll find out soon, I suppose. So yeah, this is going now. Whoa, what's going on with that loss? I may be doing target model updates a little bit too fast still. Maybe beneficial to change that. Yeah, so instead of doing target model updates every 100 steps, let's do them every 500 steps. And let's let that go. So as this trains, this is we're basically in the hyperparameter tuning phase, and that's a lot of trial and error, and it's kind of slow. And so I'm trying to figure out if I should just do multiple environments with array. This is something that will probably also come up in the future. So maybe instead of doing the stretch goal, we can add a second stretch goal. The sort of the next iteration of this project is supposed to be a more complicated project. So, cartpole is pretty straightforward. Its observation has, 4 numbers in it. The network that we're using for it is really, really small. Once you have things written correctly, you can usually train cartpole in 10, 20 minutes or something like that. It doesn't normally take very long. And so this is a good good problem to cut your teeth on, but then we want to move on to something more complicated. So the thought was to use Breakout. And what's the difference between Breakout 0 and Breakout RAM? Interesting. Let's not do this. Yeah, a Breakout RAM would probably train faster, maybe, but we'll focus on Breakout version 0, which gives an image. And so then the idea there would be to learn from the image and set up sort of a recreation of the solution of that was presented by DeepMind in their Atari paper. So while this is training, let's make sure that it's going as planned. Yeah. So this seems to be doing a little bit better. The loss is still increasing a little bit, but between every target model update, it is decreasing. We might need to make the target model update still a little bit laggier than it currently is. We'll find out, but the average reward is starting to go up. And so we can probably leave this running for a little bit. So while that is happening, let's spend some time exploring the problem that we want to solve in the future of this stream. So that would be Breakout. Let's make a new folder. Okay. Breakout. Is there an example? I guess I don't necessarily need example. I can just copy over what I have from cartpole. So import gem. And then instead of cartpole v1, the environment name is Breakout v0. And we can just explore the environment. So, I don't know, that's not going to give us useful information. I think env observation space, we can try to print that. And .action space. And let's look at what these look like. Okay, so the observation space is of type box, which I think is just supposed to represent multi-dimensional shapes. So this would be an image of 210 by 160 by 3, and then the action space is 4. I don't understand why it's 4. You just go back and forth, no? Let's see. Is there any more information on this? Atari. Breakout v0. Each action is repeatedly performed for a duration of k frames, where k is uniformly sampled from 2, 3, or 4. So there's, oh, my screen is not showing. There's some degree of randomness here, but what I don't understand is what the actions represent. Let's see. Agents. None of that is useful. What about the source code? Atari env. Actions. It doesn't list anything. I guess up and down might be an action. That's really weird. In Gym, Breakout 0 has 6 actions, and Ale Breakout Bin has 4 actions. Okay. Okay, so there's no op, which is just don't do anything. And then there's fire, which I suppose is necessary because no, it's not necessary because it doesn't start off with anything. I think those are just superfluous. So let's try to figure out which one's which, and then we can potentially just not use the fire button and just keep no op and left and right. All right. Oh, and let's check on the training. Let's see, so the average reward is steadily going up. The loss is also steadily going up. Sorry about that. I like this trend, and I like how fast the training is progressing. You know, it's hasn't been 10 minutes and it's gotten to 1 million steps. So let's give it another 10 minutes and see if the average reward keeps going up monotonically. In the past, it kept crashing, and then if the loss starts to show a stronger downwards trend, it kind of makes sense for the loss to sort of constantly keep going up in this case because by its nature, the DeepQ network is trying to model, it's trying to predict the maximum reward that you can have, and so maximum reward, as the agent explores the environment more and more, it's starting to understand that the maximum reward is actually higher than it previously thought. And that's also why it's important for it to explore the environment for longer and longer. If we introduce a discount factor, this will probably get less bad because the time horizon of the maximum reward goes down. So for the next iteration, we can try to introduce a discount factor. Okay. So let's try to explore this breakout environment. So the way I'm going to do that is by setting up a while loop. And let's see, let's render. And then let's take an input. And we'll just straight up cast it to an int. And we can then apply that to the environment. So step through the environment with the action. Let's print that and then just render it. Okay. So this should give us a controlled environment where we can sort of just go through each frame. Okay. So here's the screen for Breakout. It's a little bit small. I don't know how to make it bigger with the render command, so gonna have to leave it at that for now. So yeah, let's try, I don't know, action 0. Cannot call end step before calling reset. I did not call reset. Okay, so end.reset. All right. Action of 0. Oh, I just realized if I'm printing this, it's always going to be printing the frame as well, which I suppose is fine. Oh, and there's 5 lives total. I guess that's also represented at the top there. Action 0, action 0, action 0, action 0. So that's not doing anything. So do I need to, I think I might need to use the fire action to get the game started. Action 1. Okay, so that's why the fire action is necessary, because the game has to start. And then 0 was no op. And if I do fire again, it doesn't do anything. 2 moves the paddle to the right. And first time I called it, it only did it for 1 frame. And the second time, it seems like it did for more frames. And then 3, I suppose, is going to move the paddle to the left. Nope. Nope. 0. Okay. We hit the ball back. That was fun. Okay, so I think so. The fire is definitely necessary then. I'll have to look at how other implementations have done this. Yeah. Okay, going back to how the training is progressing, the reward seems to have stalled, but we did hit the maximum in exploration. Let's go ahead and unsmooth this. Yeah, so like a few of these examples either hit the maximum or got really, really close to it. So yeah, some of these have definitely hit 500. So this is good, I think. And the loss is also, it hasn't started a downward trend yet. It's actually getting kind of noisy. But let's give it a little bit longer. Okay. So as that is happening, I want to work on making a wrapper for Breakout and Breakout-like environments. And the reason I want the wrapper is because, at least because historically, whenever people tackle these kind of problems with simple DQN techniques or simple neural networks, they do something called frame stacking. Right, and frame stacking, if I can find an example of it. Yeah, it's like this. I think this is a good example. Or no, that's not as good one. Come on. Okay, fine. The first one was fine. Basically, at any given time, the observation for this environment is not going to be a single frame. It's going to be 3, 4, 5, or some number of frames all together, all smashed into one. The reasoning for this is because I think this one kind of shows it clearly. Let me see if I can open the image. Let's see, view image. Okay. So these 3 frames, if you just have one frame, right? Like let's say we just have this one frame on the very right, there is absolutely no way that the neural net can know what direction the ball was going. Right? It has no sense of what happened right before. This is something that you can change by adding like a recurrent layer or something like that, or giving some sort of an internal state. But normal neural networks, the one that we're going to at least start with, do not have this. So it wouldn't have the context. So that for some games, it would just be impossible to play. With Breakout, it might still work, but it would be extremely jittery. So what they do to fix that problem is to take multiple frames. The gym environment does not do this for you, right? So the gym environment is always only going to give you 1 frame. So usually what people use is some wrappers that were introduced in this repository called OpenAI baselines. And in baselines, I think it's in utilities. Or is it gym? No. Let's see, baselines, common, backend, here. So they have these wrappers for OpenAI gym environments. And people usually, like oftentimes in many different repositories, they'll just have this code copied over from the wrapper, right? And they're just going to have this environment, and it's going to have the same kind of API as the normal OpenAI gym, but then give you stacked frames. So while this training is going on, and while we sort of mess around with some other hyperparameters for cartpole, we can continue working on making a similar kind of frame stacking wrapper. Let's refresh that. Okay, so the training has started to degrade here. I'm not sure if it makes sense to give it a longer time. Okay, so before I do anything with Breakout, let's stop this and introduce the discount factor, because I feel like the issue that we're having with the loss kind of starting to go up a lot might be fixed with the discount factor. So let's kill training here. Okay. So agent.py. So the place where discount factor is normally introduced is in the train step. In the loss calculation, you leave the reward the way it is, but then in the when you look at the future Q values, you multiply them by a number less than 1, and that's called the discount factor. So we can introduce that here by just saying, let's just call it gamma. Gamma equals 0.99, which is a reasonable value. 0.99. So it looks small, but it might help stabilize some of the training. Another thing that might also help stabilize some of the training is we're tracking the total reward, right? And so the total reward for this environment has numbers like 500. Neural networks generally don't like it when you are throwing large numbers at them. And so one of the things that I did before, which did actually seem to stabilize a few things, was to take the reward after sort of we've tallied it and logged it, and multiply it by some factor. So if we multiply it by 0.1, the neural network then it doesn't need to predict, let's say, like at the beginning of the game, it doesn't need to predict like, hey, the maximum reward that you could get from here if you move right is 500 or something like that. It would be 50, right? And that can potentially help training be less noisy, right? So let's go ahead and run this again. And we'll keep everything. We'll keep just the last run. So yeah, so we can visualize both of these guys on top of one another. Let's see how this guy goes with the two changes where we made the reward, we scaled the reward down, and that should impact the loss dynamics, I think. And then we also introduced a discount factor, which should also impact the loss dynamics. So let's come back to this in about 10 minutes, and until that time, let's focus on making a wrapper for Breakout that we can use in a future stream. Okay. So I'm going to make a utils.py file. So let's sketch this out. So I'm going to start this by doing it in a stupid way, and we can then look at if there's ways to do it in a smarter way. So the main parts of the API that we care about for OpenAI Gym are the fact that once we have an environment, we're going to be calling the reset function, right, which takes no parameters and only passes back the observation. Okay. We have the step function, which takes in the action, which is an integer, and returns the observation, the reward, and I think just a dictionary. This is just some info, and that's a dictionary. And the reward is some float, and then the observation is ND array. Okay. Outside of these two, I guess there's the render function, right? But I think this can just pass through. So we could just make a really straightforward wrapper. So we can say class frame stacking env, and not even subclass anything. I know that can potentially look a little bit sloppy, but I think it can be stupid in the beginning and become smarter from there. So we pass in the environment that we're working with, right? And then we can also say noom stack or something like that. Yeah, and 4 is a good number often used, so I think that can be a good sane default. I'm just going to call it n because I think that's save some typing. Okay, so there's a few different things that we need to do here. First of all, the environment. We need to get the environment shape, right? So let's go back to Breakout. So Breakout prints out this box, right? I think that can be converted into an array. Or there's a shape property. Yeah. So that's what we need. Yeah, so self dot, not self dot. I don't think we need that. I think just hang on 1 second. So I just realized the breakout environment, the RGB pixels that's outputting, it's 210 by 160 by 3. We probably want to have some degree of pre-processing happen here. It's often like games like Breakout, because there's not a lot of so if I run this again, there's not a lot going on here, right? So a bunch of these pieces are multiple pixels, but they don't need to be. So we can effectively resize this. However, resizing is relatively straightforward to do with something like OpenCV, but as soon as you I think it becomes a little bit more complicated if it's not a 1-channel or a 3-channel image. So we can, for now, make this. So instead of saying just frame stacking n, we can say frame stacking n, resizing n, and we can specify a parameter like parameters that have to be passed, which would just be like width and height. And when we work on actually trying to solve this with the DQN, those guys would probably be the same number. It would probably be 84 by 84. It's a fairly commonly used number. And now we can set like self.w equals w, self.h equals h. And now we can define a buffer that's, yeah, and I'm not going to leave any of these as color as well. But we can define a buffer that is, this width, this height, and then depth would be equal to stacking. Okay. I'm going to import OpenCV. Okay. And then the buffer is going to be self.buffer equals np dot zeros, right? And the shape is going to be height, width, and new stack. Yeah. Okay. And then the dtype is uint8. We can also add a private use function here. That's just pre-processed frame. So whatever frame is received from the environment, we want to take it and run 2 operations on it. One would be resize. Right, so resize the frame to the new size, which is going to be self.w, self.h. And then the second operation is to change the color space. So image equals cv2.convertColor, image cv2.color bg, that's RGB to gray. I'm pretty sure the OpenAI gem outputs the image as RGB, not BGR. BGR is the standard for OpenCV, but I think everything else uses RGB. I guess we'll find out. So image equals cv2.convertColor, all of that stuff, great. And then just return image. Okay. So now we can define these expected functions. So if somebody calls render, first of all, so we are just going to call this and be done with it. Right, so that's straightforward. This will only give us the latest frame. If somebody calls reset, that's not supposed to take any parameters. So now, yeah, so reset is the opportunity for us to fill up the buffer, right? And then every time we call step, we can sort of move the buffer so that older frames go to lower channels, right? So we have to define some sort of semantics here. So let's see. 0th frame is latest. First frame is the one before, etc. Right. So now if we call reset, we can call self.m.reset. So and then preprocess it. Right. And that should give us a resized single channel image. And because this is a reset, we can now set self.buffer. Let's see. 0 equals m. Yeah, I can just do stacking. So I can just do np.dstack self.n. Right, that should work. Okay, so set the buffer to this, right? So this is only going to happen at reset, and then return the buffer. Because we're going to be mutating the buffer inside, instead of returning the buffer, we should return a copy. Does this get me in trouble? It gets me in a little bit of trouble because we're going to have things that could have been just pointers are going to become copies, but I think that's a necessity. I guess we'll see. Okay. Let's finish the step call and then we'll check in on training. The step call takes in an action, right? And so we need to get the image, the reward, and the info from the environment. Same thing with the image now. Pre-process it, right? But now we need to, so let's see. So we need to take the buffer and shift things down. So we want to set -1, no, negative self, no. Okay, if we have 4 frames stacked, we want to take frame 0 and set it in the 1 position, frame 1 set it in the 2 position, frame 2 set it in the 3 position, and frame 4 goes away, right? So what we're doing is we're setting -4, no. Oh my God, this should not be this difficult. Yeah, I think it's -4, so it's negative self.n all the way to -1. No, that is incorrect. Let's see. We're taking 2, or 1, 2, 3. Let's see. 0, 1, 2 are being mapped to 1, 2, 3. Okay, so 0, 1, 2, we want to set at 1, 2, 3. Okay, yeah, I was thinking of it backwards. So we actually want to go from 1 to self.n and set that equal to self.buffer 0 through self.n minus 1. Right. And now the 0th position can be taken over by this new image. Cool. And then we can return self.buffer. We can return its copy. We can return the reward and whatever info was coming through. Oh, I totally forgot done. Okay, so let's check in on the training. And it did not seem to have the same kind of effect that we were hoping. Well, I was hoping. And one of the things that I'm starting to notice now is there is, like, after the epsilon value starts to become really, really small, we start to see this degradation, right? And it seems to be pretty intense. And then loss is having a very similar kind of behavior. If you turn on the last attempt, you know, loss had a similar kind of effect where it started to sort of grow really fast, right? I kind of want to leave this for a little bit. It did have this point where it was hitting the max score a fair amount of time, but it was still an epsilon value of 0.2. So that's not particularly encouraging because, you know, it's a combination of 20% random play. We want it to be doing well without random play, right? So let's leave this training for a little bit longer. Let's see what happens once it gets to like 4 million frames or something like that. And in that time, we can test the breakout wrapper. Okay, so to do the test, I can do that for now in a main function. Okay. So we make the environment, and now we're gonna essentially take a reference to the frame stacking and resizing environment, pass it env, and for giggles, let's make the image really large, just for fun. And num stack we can leave to 4. Okay. So what I want to do now is do the reset. And then for I in range, m.shape -1. Let's just save these. I find that to be often the easiest way to debug systems like this is to just save out the images. Right, and that's going to be M and then I. Okay, so let's run this guy. Ah. So I'm going to have to come back to this. There's a little bit more to it that a few things that I didn't wrap, and one of those is observation space and action space. I'll return to this. Okay, so let's go to temp. These images are here. Okay, so yeah, we got frames from Breakout, and they look fine. Actually, instead of saving multiple images, let's go ahead and trash this. Instead of saving multiple images, it may be more educational to save a single image. You can leave this the same way. Make an array, ims.append. Right. And then write, let's see, based on some index, we'll essentially do an h-stack. So np.hstack of these images. And then it'll give us sort of a reel that we can look through. All right, let's go back to temp, 0.jpg. Yes, this is what I wanted. So right now, this is just a reset, so these frames are the same, right? And so if we go ahead and now set up not a while loop, so let's do for I in range 10 frames, right? And in those 10 frames, actually even before that, we can do random actions. So actually going to put this on pause for another second. Going back to the training, so this is not working. We have sort of good performance up to here, and then things start to degrade really badly, and the loss just sort of keeps going up. So there are a couple of different things that we can look at. One of them is epsilon decay. So we can potentially make it so that the epsilon decay is even slower than it is right now. Another one potentially could also be learning rate. It's not something that we've messed with at all, and we have a fairly small learning rate, so that might be an issue. So like the bad scientist that I am, I'm going to change both of them at the same time, and hope for the best. So the epsilon decay, I'm just going to add another 9 to it, and that'll slow it down to some extent. And oh, okay, yeah, we should do it this way. Okay, so, and then I can sort of explicitly pass it. Cool. So now epsilon will decay slower, and we'll have a faster learning rate, and see if that changes anything. Whoops. Wrong file. Oh, this is unfair. Okay, I have to take a moment here. It was starting to do better. Okay. So I guess things were fine. Let's see. Yeah, it was going back up. The loss was starting to come down. I didn't look at it before I killed the training. I suppose patience is a virtue. No matter. Let's let it run again. We'll go back to doing the breakout stuff, and see if the changes did anything. Because again, like I said, there's the physical amount of time that it's going to take for something to train, but there's also the total number of whatever operations are going on. So it would still be interesting to see how that changes. Oh, what we could do, however, is we could run a test using, because I've been saving models in a very unintelligible way, but I've been saving them. Nope, wrong weights. Let's see. So if we look at, this is one of the things I really like about weights and biases. You can look at absolute time, right? And so I can see that this increase in performance, this peak started happening around 11:40 p.m., right? And so 11:40 is this file. I should probably have a better naming convention, but whatever. So let's run a test. That was the wrong folder again. So one of the things that I haven't done is I haven't really made this a nice CLI yet. So let's change that. If folks have seen my Python libraries videos, they would know that I like the arg library. And with that, all you have to do is just say arg.dispatch command, right? And pass it the name of the function. So now if I do, not models, just agent.py, it's just going to run. Interesting. Did it not save? Oh, no. This is correct. I am very confused. Let's check the diff, make sure. Yeah, I'm saying I'm importing arg. And I'm not calling it right in any way. Can get rid of these guys too. Let's try this again. Oh, they have defaults. That's why. Okay. Sanity restored. I added defaults. Which, yeah. I can't really get rid of any of them. I can give it a name though. So I can have a required argument called name, and we can pass the name here. that would work. So now it should just spit out the help. Okay, so now I can sort of from the command line say run a test, give it a checkpoint file. The path to the checkpoint file would be home jack rl, or no, not home jack. I can just say models, and the model name from 1140. And then the device, I want this to remain CPU. Following arguments required name. Name in this case does not actually matter because we never go to WANDB, so I'm just going to say void. Well, it's keeping it balanced, but it's just accelerating to the right. Okay, so I was probably getting a little too optimistic about that spike, but it was improving. I can try a different set of weights as well. Yeah, this one actually is doing a little bit better. It's not moving as fast, and it's kind of doing a shimmy back and forth. It's still going all the way to the end, though. Yeah, it hit the score of 500, so I can't fault it for anything. There's no negative reward. This is one of the things that you have to be kind of careful with reinforcement learning. There is no negative reward for not staying in the center, right? There's no additional feedback signal. So if it has like a bias towards one side, but starts to achieve really high scores towards that one side, it's not going to care, right? So that's fine. Okay. Yeah, so this was the mistake run. Okay, so the new run that we have started is not at all going the way that we had hoped. So even after 1 million steps, it's the reward is not increasing at all, and the loss is just sort of shooting up. So what was the change that I had made for this? I totally forgot what the change was. Oh, it was the learning rate. It was the learning rate and the epsilon decay. And so I have a feeling that some of this slowness is happening because of the epsilon decay being way slower. So let's bring that back down, or back up, I guess. And start this again. And I'm going to leave because it was starting to improve. We were just about to start improving again, but this was a little bit too slow, and that I think that has more to do with epsilon than it does to do with the learning rate. So let's figure that out. Name. I can start giving more descriptive names to these runs now. So I can just say higher LR. Okay, so we'll come back to that in about 10 minutes. Let's continue working on Breakout. Do it. Oh my god, I should be using i3. Okay, so Breakout. So to make sure that value did get reset, it did. Okay, cool. Okay, so we were running a test of the frame stacking utility. So for 10 iterations, we want to take a random action in this case. So a rand int between 0 and 4 in this case. And let's get the image and then ignore everything else. And before this, I do want to do one other step from the environment because we need the fire operation to run. Otherwise, the game won't start. And I think we might need to do this as part of the reset. We might need to ensure that that first action takes place. Otherwise, the training might suffer. That's, of course, going to happen in the future. Okay. And then instead of rendering, we're going to do the same thing here. Okay. Not I. Actually, this does not need to happen. And we can just say idx plus equals 1 here. Okay. Let's run this, and that will tell us if the frame stacking is working as intended. Could not broadcast input array from shape 3484. What? Oh, I did this completely wrong. Here we go. Better. Index 4 is out of bounds for axis 0 with size 4. Oh. The 4 is inclusive. What? I got rid of that. This is line 57, random to... No, I got rid of it. What? Are my files not saving sometimes? There we go. I feel like my files aren't saving sometimes, which is weird. Okay, let's go to temp, and let's look at some of these images. So this was frame 0. Nothing was happening. Then we did the fire action. Okay, that's bad. That's significantly more frames than there should be. So what did I mess up? Let's look at step. I did the pre-processing. That should have been single channel now. I guess we can. So we know the reset is correct. So the problem with this step. So we can try to print the buffer shape. This should not change. Or am I? Oh, never mind. My wrapper is probably fine. I just wasn't reinitializing this images array. Okay, so frame 0, frame 1. So the frame on the left change, right, between, oh, it's not 1. Oh yeah, it's 1. So between 0 and 1, the frame on the left changes. And then between 1 and 2, and the 10 gets in the way because computers count weird. Let's just get rid of it. So between 1 and 2, so this frame, that was in position 1 for frame 1. Let's see, 0. No, this is 10. Sorry, let's start this again. 0.jpg, all of them are in the same place. 1.jpg, the first frame has moved. 2.jpg, the first frame has now moved to the right, and second frame has taken over. 3.jpg, same thing, same thing. Okay. This these random actions don't seem to be very random, but this is working as intended. Right. So we have the frames stacked as we want them to. Appears to be working correctly. So I think this is a good overall setup. I still need to properly wrap the observation and action space, but this frame stacking and resizing env thing is a good overall setup for us to train on Breakout the next time. Okay. So yeah, it's about midnight here, so I think I'm going to end the stream soon. I just wanted to take a look at training again. The loss dynamics haven't really changed with the higher learning rate. The reward dynamics also haven't really changed, as far as I can tell. I guess they kind of have. It's it peaked a little bit earlier, which it never did before. So yeah, let's take a last peek through the various hyperparameters and see what else we can potentially change to try to get this behaving a little bit better. So we tinkered with epsilon decay. I'm convinced that was too slow. We definitely could have a larger sample size, which will slow down overall training, but should help make the loss a little less chaotic. So that's one of the changes that could potentially help. I don't know if I buy anymore that this scaling is really doing anything. I feel like anecdotally it should do something, but I don't. I'm not wholly convinced of that. I guess this is it. The one other thing that I haven't considered is the model architecture. But this is such a simple problem. I feel like I felt like 256 was already too big. So for us to increase that number to make the model bigger, I'm not necessarily convinced that would help. But that's another thing that I could potentially try at some point. Okay, so I think with it essentially being midnight where I am now, I'm gonna stop the stream at this point. The main goals, that's also done. So the main goals were put the network on CUDA, make the replay buffer faster. We've done both of these things. The total training speed is at least, in the later stages still 3x faster than it was, excuse me, than it was last time. So that's a good overall improvement in my book. In terms of hyperparameter tuning, so far there isn't really a combination. We've definitely learned the which ones are bad, but we haven't quite found a combination that makes the training go much faster. But even without these, the environment is getting to a really good point. We'll probably revisit the idea of multiple environments generating data in a stream related with Breakout. But we did put together the frame stacking wrapper for Gym that we can use for training Breakout. So I think the next stream is going to be focused on writing a convnet and then setting Breakout up for training and then running that. And sort of that's probably going to take a little bit more fiddling as well. So that's all I got for y'all tonight. Hope this was interesting and potentially useful for people. And until next time, bye.